Okay, so today what we're going to do is we're going to go through kind of TCPIP programming. Previously we looked at kind of the OSI model, then we looked at TCPIP at a low level, kind of like how the packets get formed, how they get layered. Today what we're going to do is we're going to look at programming TCPIP. In other words, we want to write code that actually talks over the internet to other devices. Other device could be a server somewhere, could be some sort of physical device, an embedded system, but they all kind of work the same way. So let's take a quick look at how we're going to go through programming this. All right, so the first thing, we looked at that kind of layered model. We saw there was a TCP layer and there's an IP layer, which is why it's TCP/IP. And we looked at the headers of those layers, the TCP header, the IP header that adds the addressing, and then we also looked at Ethernet. But what we're going to do today is we're going to look at how to program that. And when we program that, we don't really have to worry a lot about the low level, how it works, how the packets get made, how they get sent, how they get received. We don't have to worry too much about that. Although understanding how addressing works can help, understanding kind of the concept of ports can help. We don't have to worry about where those things are in the header. We don't even really have to worry much about it except for conceptually knowing that it's there. So in order to program this, though, we really need to understand how the library works that interfaces to those things for us. So there's a library that's already built. We don't have to build the packets ourselves. We don't have to manage the flow ourselves. That's done for us in a kind of TCP/IP subsystem, the networking subsystem. And the library we use to interface to that subsystem, though, is called the sockets library. So that's what we're going to look at today. All right, so first off, socket programming. And in practice, what we're going to do is we don't have to worry too much about any of the low-level stuff. Like I said, we just have to worry about how do we talk to the sockets library. So let's take a quick look at that. All right, first off, sockets, I guarantee you've used sockets somewhere today. Actually, watching this video, there are sockets going on to show the video on YouTube. There's sockets going on for you to log into the course site. There's sockets to get on a web page. Pretty much sockets are one of the most widely used communication methodologies that there is. And there's a historical reason for that. We're not going to get too much into the history of this, but the sockets library is kind of this really kind of extensible library that can be used for a whole lot of different things. The internet, TCP/IP is based on it, but you can also do other things as well. Control area networks, low-level packet drivers. There's just a ton of different network technologies that can sit underneath the sockets library. It's designed to be a library that can be used for a lot of different things. But it also happens to support TCP/IP, and it also supports UDP. And the difference between those two, TCP is kind of stream-based. In other words, it's reliable. You set up a connection, like a phone call. You put messages in, they come out the other end. It's guaranteed to kind of ensure the reliability of the transport. It's also guaranteed to ensure the sequencing of the transport, where datagrams are more like postal mail messages. We drop them in the mail system, they get to the other end, but some might get lost. The order you send might be different than the order they received, and so forth. Now, web browsers, web servers are built using sockets programming. The internet itself is largely built on TCP/IP, and sockets being our interface to that means that's how we're going to write stuff that exists on the internet, is using the sockets library. Okay, now first off, if we're going to be talking about a socket, what is a socket? And a socket, the best way to think about that is it's kind of our connection to the networking subsystem on the machine. So think of it like a electric outlet on the wall is your way of plugging in to get electricity. A socket is going to be our way to connect to the networking subsystem, and that could be TCP/IP, it could be IPX, it could be a lot of things, but the sockets library allows us to access a lot of different networking methodologies. We're just going to happen to use it today for TCP/IP programming. All right, so before we do anything else, we have to create a socket. The next thing that we have is that any subsequent call after we create that socket, we're going to use that socket to make that call. In other words, we're going to say, give me a socket to talk to the networking subsystem. After we have that socket, we're going to say, okay, set up that socket to do things with a certain networking type, and so forth. So the original Berkeley sockets library was written in C language for Unix, and it's called the Berkeley sockets library because that's where it was built, University of California at Berkeley. And many years ago, they sometime after TCPIP was created, they created this library for interfacing with it. And it's been refined over the years, but it's largely the same. So we're going to start with looking at how the sockets library works in C, C++, mostly C. And one of the cool things about most Unix installations is they have a thing called man pages. And what man pages are really manual pages. So imagine like a user's manual. You have this bunch of papers that has information on it. That's the kind of thing that's in a man page, except it's all in an electronic format that you can look at. And if you have a Linux box or access to a Unix machine, you can go to the command prompt. You can type man and then space, and then type in socket, and it will show you the man page for the socket function. The man pages are divided up into different subsections. We'll talk about that in a second. Kind of as a programmer reference part. There are user command parts, but if you just do man socket, you'll get the manual page for that. Now, one thing, if you don't have a Unix box set up, you can still look at these functions. And let me kind of quickly show you how you would do that. Hold on one second here, and I'll bring up a web browser here. So let me switch to the display. So here's just a Chrome window. So if I type man page socket and hit enter, Google will see this socket and then 2 in parentheses. That 2 is kind of the programmer reference part of it. So if I click on that, here's the man page, what the man page would look like for the socket function. Notice it's kind of just like a simple description, kind of like an API reference for that. But you'll notice here, let me zoom in on that a little bit so it's a little easier to see. And what you can see here is, oops. Okay, well, let me use the arrow keys. All right, so zooming in on that, you'll notice it has the name of the function, a description of the function, and then down here it's like the function prototype. Here are the include files that you need to include to access this function. And then down here is a detailed description of it. So what I've done is I've distilled some of this stuff and pulled it into the things. But one of the cool things about the man pages are that they reference other functions that you're going to need to use to do things. So you'll notice in here, it's got a ton of information here. But notice down here, these things that show kind of in this blue section, you'll notice that, for example, it says sockets of type sock stream or full duplex streams. It describes that. It says you can, once a connection to another socket is created with connect. And we can actually just, on this man page in an HTML format, I could just click on that and then read about connect. And I can use back, and I can come and read about read and write and send and receive and close and really get proto-end protocols. And you could go to any of these sections. Now notice a good number of these are in section 2. That's the programming reference, but some of them are in other sections like 5 and 3. So just keep in mind that the man pages are available. They're easy to get to. And if you already have a Unix installation, you can just get these directly from that without ever getting on the internet and without doing a web search. Now I'm going to pull parts of these man pages into our presentation as we go through the class. Let's go back to the presentation for a second. All right, so now back in the presentation, we've got this concept. Before we do anything else, we have to create a socket, and the socket function is what does that. So let's go ahead and go out. So looking at that socket man page, it says the socket function creates an endpoint for communication, and that's what we were talking about with having to call that before we do anything else. Having to create that socket is we need to have a way to talk to the networking subsystem, and creating a socket gives us that kind of connection into that subsystem where we can do that. Now, notice that in the function prototype, the socket function accepts has 3 parameters that we need to pass to it, 3 arguments: domain, type, and protocol. And then it returns this integer. And what this integer that it returns is that's going to be the socket that we get. It's kind of a descriptor for the socket that we're going to use. And it says that on the next line here. Socket creates an endpoint for communication and returns a descriptor. Now, let's take a quick look at the parameters and what it expects for each of those, because that's going to be something that we're going to need. So looking at that, let's start off with domain. So socket in domain, notice it takes an integer. It says the domain argument specifies a communication domain. This selects the protocol family which will be used for communication. These families are defined in sys/socket.h. The currently understood formats include, and notice that again, like we said previously, that there are a large range of these possible kind of domain types. The one that we're going to use is going to be AF_INET, and that stands for Address Family Internet. This is IPv4 protocols. And notice there's a man page for that. In the manual section, it talks about the IP packet types. So you could look up more information on that if you really wanted to. But notice that there are other ones here, AF_Unix, AF_local. Those are kind of local communications using something like a named pipe, for example. There's IPv6 support. There's IPX, which is a Novell product. There's Netlink, X25, AX25, ATM, PVC, Apple Talk, which is an old Apple communication thing. And then this AF_packet is kind of a low-level packet driver interface. And there may be more of these in your thing as well. The one we're going to use, AF_INET, because that's what we're going to use for TCPIP. All right, going on to the next parameter there is that type. And type says what kind of communication semantics do we want? In other words, is this going to be a stream-based protocol where we open a connection and it handles the reliability? Or is it going to be a datagram-based thing? And also notice there's a sequenced packet, there's raw, this reliable datagram layer that makes sure the datagrams get through, but the ordering might be off. So there's several of these. The one we're going to end up using for TCP programming is sock_stream. And notice, let's focus on the description of that. It says provides sequenced, in other words, they're in order, reliable, meaning that if any get lost, it automatically fills them back in. Two-way, so we have this stream where we can put stuff in one end, it comes out the other end, and then vice versa. So it's kind of a two-directional stream that we can talk to, like a telephone. And it's connection-based, meaning we connect. Once we're connected, we can exchange data. When we're done, we disconnect. And notice that the main components of that, it's a lot like a phone call. You call, somebody answers, you talk while the connection has been established. When the connection is done, you terminate the communication, but it's reliable, two-way, sequenced. For example, on a telephone call, you don't say a sentence, and sometimes the words get jumbled up in a different order. On the receiving end, it's exactly what you said is what comes out, and it's connection-based. Now, behind the scenes, it's still packet switched. It's based on an IP packet network, but it handles all of the verification and sequencing for us. We don't have to worry about it. So that's what we're going to use. Now, also notice there are a few additional things we can add on here. We're going to talk about these later on in the semester, especially the sock_non-block. That can create a non-blocking status flag for that file descriptor that gets opened. So, for example, when we try to read from it, if nobody's talking, it won't block and wait. So we'll talk about that a little more later. But right now, just note that for domain, we're using AF_INET. For type, we're using sock_stream. Later on in the semester, we're also going to use sock_dgram, which is a datagram protocol. And notice that that's connectionless, unreliable messages of a fixed maximum length. So why would we want something that's unreliable? And the answer would be for high performance, for speed. That there's a cost to having this layer ensure that all of the data gets through correctly. And in some cases, that latency added by this might not be wanted. A good example of that would be like a game server. We just want to send out messages of the game state for over and over and over again. And if a few get lost, then there'll be another one behind it that updates the game state to the more recent thing. And so this datagram thing, and notice there is this middle ground down here, this sock_RDM, which is a reliable datagram layer that guarantees delivery of the datagrams, but not necessarily the ordering. And this is actually faster than sock_stream and has some advantages over sock_stream, but it also doesn't have the disadvantage of unreliability, but it's a little slower than UDP using datagrams. Again, we'll talk about those things later in the semester. Okay, the final argument up there, protocol. It says the protocol specifies a particular protocol to be used with the socket. Normally, only a single protocol exists to support a particular socket type with a given family, in which case the protocol can be specified as 0. Now, some protocols do have, or some domains and address types have different protocols that are supported. In our case, notice that if there's only one, we can just say 0. That's kind of the default one. Now, down here is a paragraph that I pulled out of the man page that I think is important for us to read because it's going to lead us to what to look at next. So it says sockets of type sock_stream, which is what we're going to use, are full duplex byte streams similar to pipes. So we've the concept of pipes is kind of just this two-way connection. Stuff goes in one end, it comes out the other end, but notice it's bidirectional. It's full duplex, so stuff that goes in the other end comes out this end. So in other words, we have this connection that's created. We can stick data in one end, it comes out the other end, no matter which end we stick it in. Now, one thing though, it says, and this is going to be important to us, it says that sock_stream connections do not preserve record boundaries. In other words, if I write in a giant message, it might not send all of it. It might send part of it, and then the other part of it we'd have to send later. Or I might send 2 messages, one and then the next one. They'll all get run together on the receiving end. Think of it just as a stream that data goes through. It doesn't treat it as here's message 1, and then here's message 2, and here's message 3. It'll always preserve the ordering, but they can all run the data for all of them can run together on the receiving end. There's no delimiter or divider between here was the first message, here's the second message, unless we build that in ourselves in some way. Now, it says a stream socket must be in a connected state before any data can be sent or received out. In other words, if I just pick up my phone and start talking into it, hello, it's not going to go anywhere. I have to connect first, wait for the other person to accept the connection and answer, and then we can have our conversation. So we have to have the socket connected before we can send data or receive data. And notice that then it gives us some hints as to where to look at next. It says a connection to another socket is created with connect. Once connected, data may be transferred using read and write. There's also send and receive that we're going to look at. And it says, or some variant of the send and receive calls. So those are possibilities for talking over the connection once it's been made with connect. It says when a session has been completed, a close may be performed. And it says also out-of-band data may be transmitted as described in send to and received as described in receive. And this send and receive that are kind of listed here, this out of band, means that you can have a stream of data and you can send other information that is kind of not part of the stream but may be important to the receiving end. And we're not going to look at that today, but that can be useful for certain applications where you want to have the main stream content, but then you want to have other data about keyboard state or like maybe in a chat or something go through as well without having to insert it into the data yourself. Okay, now to finish that up, continuing that description where we left off, it says the communication protocols which implement a sock_stream ensure that data is not lost or duplicated. And that's what we said that the TCPIP layer was doing for us. And I'm not going to read the rest of this stuff right now. You can look at the man page if you want. But also notice I put sock_dgram down here. It says those allow sending of datagrams using send to and receive from. Later in the semester, we're going to come back to this datagram methodology of doing this because it's faster and useful for game kind of server or real-time server programming. So the idea here is send to and receive from are different than send and receive that we saw in the previous one. So datagrams are sent and received differently than streams have data sent and received on them. Okay. So the return value of the socket function on success, it will return a file descriptor for the new socket that's returned. And think of a file descriptor as just a file handle when you open a file. So in other words, when you open a file, you would use like fopen, for example, in C, and then that would return this file descriptor. And the file descriptor kind of has a number associated with it, the number of the file descriptor. And then you can, once the file's open, you can use the file. When you're done, you close it. The same thing is true for these sockets. So it works a lot like reading and writing to and from a file. But notice that if it fails to open a socket for some reason, it returns a -1. So when we try to open a socket, we should probably check that return value. And if there is an error, then there are a number of possible reasons for that error. Some of the common ones I've listed here. But for example, you try to open a TCPIP connection, sock_stream with AF_INET on a machine that doesn't have a network card in it, then you're going to get this kind of implementation does not support the specified address family that we tried to open the stream for. So if we're on a machine that doesn't have that, it can return, I don't have that kind of network for you to open. But there's a number of them here. You should maybe just print out the error message, an error message with the error code or log it if it fails. But we should check that return value. Okay, so in other words, for our purposes, we can create that TCP socket like this. So notice that we're just calling the socket function down here. We've made a variable to keep that integer that returns in, to keep that file descriptor in, called mySocket. There's really no reason to initialize it to 0 here. We could have, because we're setting it, assigning it on the next line. But anyway, that does show that it's just an integer. So I call socket, I pass in AF_INET, I pass in sock_stream, and I put 0, which gives me the default one, which is going to be TCP. And then the next line, we could have done this all in one line, but to make it a little more clear, I separated it. We could have just wrapped this entire thing in this if statement and said that whole thing equal -1. But I just decided to check it on the next line. And here, if the socket wasn't open, we should probably handle the error there. Print out a message, give the user, we shouldn't try to use the socket if it failed. So if we get past this if statement here without it going into there, then we know that we've opened the socket successfully. Notice if we wanted to use UDP, datagram, instead of a streamed connection, it looks exactly the same. The only difference is we put sock_dgram there instead of sock_stream. Those are the only things that change between the two code sets. So if I want a TCP connection, we create a socket like this. If I want a UDP connection using datagrams, unreliable but faster, I create it like that. Now we're going to focus the rest of this class on looking at TCP connections. So we're going to create a socket like we have up here on the top version. Okay. Now, one of the things we have to decide in socket programming is TCPIP is kind of a client-server architecture. In other words, if we're going to have a connection between two machines that's over a TCP connection, a stream connection, somebody has to be the one making the phone call, somebody has to be the one answering the call. Same thing with like a normal telephone. Somebody has to dial the phone, someone else has to hear it ring, and they have to answer it. So we need to decide when we write our code, are we going to be a client in this program, a server, or both, depending on the situation. But the difference is how they use that socket. So a server is going to use its socket to listen for incoming connections and then accept them or answer them when they come in. And a client is going to just kind of make the call. It's going to connect to some server that's listening somewhere else. So once they're connected, however, the data exchange can go either way. It can go from client to server or server to client, or it can actually switch partway through. This client can ask the server a question, the server can provide an answer, and when the conversation is done, when they're done exchanging data, they can just both shut down and close that connection. So again, think of it like a phone call. Now, one thing about that is that's also, we mentioned this earlier, this is how web servers work, and a web browser. The browser is the client. The web server is obviously the server. You type in a URL in your address bar of your web browser. It connects to the listening server. Once they're connected, the web browser requests a particular page at a URL. The server then, if it has that page, it returns the page back to the server or back to the client. The client then renders it in a window, so you can see it in Chrome or Firefox or Edge or whatever browser you use. And then the connection gets closed. So that's the idea of what we're talking about here. Is somebody has to be listening. Somebody has to make the call. The listening one has to accept the call. Once they're connected, they can exchange data either way until they're done, and then they can close the connection. Okay, so again, with socket programming, one machine has to be listening, which is the server. The other has to be connecting, which is the client. So we need to take that into consideration when we're designing our code or writing our code for this. That there's another thing here to note that one server can handle multiple connections from multiple clients. Again, like think of a web server. Google.com that we just used to look up the man page. It's handling connections from people all over the world right now doing web searches, looking for results from that. But we're going to start off looking at the client, which in this diagram is over here, which is simpler than the server. There's a few less steps here, but notice both of these start with socket. So that says socket, that says socket. They both start with creating a socket. And then on the client, we connect. After we're connected, we send and receive. Here it says write and read, but here we can think of it as receive and send. And then when we're done, we're going to close the thing down. We're going to talk about that later. There's a few more steps on the server. We'll come back to that in a second. Okay, so the client connection, in order to connect, we're going to use the connect function. And here's a little part of the man page for the connect function. Again, if you want to look at the full man page, you can go back to the kind of man pages here, and notice that I could go back and actually I could just click on where it had connect in here, which is right there. Or I could just do a Google search for that. So if I click on connect there, notice here's the full man page for the connect function. Everything that we would ever want to know about how connect works. So really a lot of useful information here. And one of the things that's cool about these man pages is you don't really need a tutorial or anything. You could actually learn how to do socket programming just from these man pages. And if you had like a Linux box set up, you could just type man, connect. It would show you all this information. If you forget how one of the functions works, you could look it up. Very easy to learn a lot from these man pages. All right, let me switch back to the presentation. All right, so again, I've distilled parts of those man pages out that are going to be of interest to us as we go through this. So start off, connect. It says initiate a connection on a socket. So in other words, that's like make a phone call on the telephone. All right, so how does it work? Well, we have to first we pass in some arguments or parameters, and it returns something to us. So what we pass into this, the first thing is a socket file descriptor. The second thing is we pass in this struct sock ADDR address structure, and then we pass in the length of that address that we passed in. And notice it says that down here. It says to connect, or the connect system call connects the socket referred to by the file descriptor sockfd to the address specified by ADDR. The ADDR len argument specifies the size of ADDR. The format of the address in ADDR is determined by the address space of the socket, sockfd. In other words, the address family determines how we set up that address, because remember, the socket library was designed to work with a number of different possible addressing systems. The one that we're dealing with here, TCPIP, so we need to set that up to be an internet type address that we pass in a pointer to the structure of that here. And we're going to see that in our code later on, and this is going to be the size of, or the length of, that address that we passed in. Now, the rest of this we'll skip over for now, but notice it says return value. If the connection succeeds, when we try to connect, it says 0 is returned. On error, -1 is returned. And that's a theme we're going to see throughout the sockets library, is whenever there's some sort of failure, we're going to end up getting this kind of -1 returned to us, and then an appropriate error message value set in this error no global variable. All right, so the idea here, pretty simple. We call socket, that returns to us a socket file descriptor if it succeeds, and then we pass that into here along with the address we want to connect to. We'll talk about how to fill that in a little bit later, and the length of that address, and then that's going to connect. And if it connects, it returns a 0. Otherwise, it returns a -1, saying I couldn't connect to that machine for some reason, and we could figure out the reason by looking at this. Okay, so here's my client code now. So let's take a look at this. Here's the socket part we had earlier. None of that's different. But notice I've added this structure declaration up here, struct sock addr underscore in. And what sock addr underscore in is, it's basically a structure that is specific to the internet. This IN stands for internet. So this is an address for an internet thing. That's the structure specifically for those. Remember the function though, if I go back to connect, let me go back for a second, notice it says of just sock addr pointer, not sock addr underscore in. So this is kind of the generic version that they have inside of the function call, but we're going to fill in the address with a specific internet type here. And that's already been built for us. This structure already exists. It's been created. It's in one of the header files, so we can just use it. And notice that this is the server I'm going to connect to, or the destination that I'm going to connect to. I've called it server here. But that's the, for example, if I wanted to connect to some other machine somewhere else, that's the server. I'm the client. I need to know the address of that server I'm going to connect to, which is why I call that server. So now to fill, after the socket gets created, I fill in the address structure. And you notice I fill in it has several sub parts of it. It has a port, it's got the address family, and it's got the address itself. And notice I filled in the address using this function inetaddr, which lets me put the numbers and dots notation in. And this I did a name lookup. This is actually a Google owned server, 216.58.214.78. I just did a lookup on what addresses google.com show up as, and that's what I came up with. So I just plugged that in. And port 80 is the standard HTTP port. So in other words, I'm not having to worry about writing the server. I'm just connecting to a server that Google already has. And that shows kind of the power of TCPIP is I can write a program that connects to someone else's server that they wrote. And I don't really have to know much about their code except what address they're on, what port they're on. And then once we're connected, obviously I have to know what the format of the protocol is to do that, which is why the internet exists, the World Wide Web exists, is HTTP has kind of a standard open way of requesting web resources and having them sent to you. And if everybody uses the same rules, then I can make my program connect to Google and get search results from them if I wanted to. Okay, now continuing on, after we have the address structure filled in with the address and the port and the address family that we're connecting to, the next thing is to just call connect. And notice, like we talked about on the main page, I pass in the socket that was created up here. And then I pass in the address of the structure that I filled in here. And because it's expecting a pointer. But notice that I have to cast it as a struct sock addr pointer. And again, the reason for that cast is the reason I need to cast that as that pointer type is because, remember, this function is kind of a generic function for all kinds of different networking, not just TCP/IP. Socket library works for a lot of different network types, so we have to take our specific type, we're casting it as struct sock addr pointer, the generic type, and then we're passing the size of that and how big is this structure, because that's what it wanted in that position. Now, one of the things that I have here is I put less than 0 here, but you could say not equal -1. So if that's not equal to -1, then it failed. Just print out an error message. And if that does succeed and I get down to here, then I know that I'm connected. So at that point, if I get to this line of code here, this printf is connected, I have now successfully connected to, in this case, this address on that port. All right, so now that I'm connected, we need to exchange some data, but let's look at the other side as well. So let's say we want to write our own server. So before we look at exchanging data, what would it look like on the server side? And remember that diagram back here a little ways. Oops. This one, notice it's a little more complicated, that we have a socket, same at the top, but now rather than just connecting, we have to bind, listen, and accept. So it's kind of this 3-step function call step process up here that we have to go through on the server side. So let's go ahead and go back to that. So on the server side, like it says here, things are just a little bit more complicated, but not too much so, that we need to use bind, listen, and accept to complete that connection. Now, what do each of those do? Bind essentially is the first step. And what that does is it essentially associates the socket that we already have opened with a particular address on the local machine. And so we need to say, hey, this socket, bind it to that address. So in other words, you might have servers or systems that have more than one connection to the internet, and you might have more than one network interface, so we have to pick which one we want. So in this case, that's what bind does. It says, associate this socket with this network interface. After we've bound, and that has proven successful, the next thing we want to do is call listen. And what listen does is it essentially is kind of like exactly what it says. It causes that socket to start listening on that bound address port for an incoming connection. So listen is our way of saying now, wait for that phone call to come in or that connection to come in. And then when it does come in, accept is how we accept it. And what accept does, we'll look at that in a little more detail here in a second, but it kind of blocks and wait. If we could call accept when there's no connection that is, the phone isn't ringing, it essentially says accept a call. It sits there and waits for the phone to ring. As soon as it rings, it accepts it and then allows you to start talking thereafter. But I need all three of those steps. So let's look at each of those in a little more detail by looking at the man pages, parts of the man pages for those. So let's start off with bind. So bind says bind. It says name in the description, but it's really an address to a socket. So in our case, notice the socket that we've already opened, and then the address we want to bind it to, and then the length of that. Notice this looks very similar to connect, and it really works the same as connect. The only difference here is this, when we bind this, is not the address of a machine somewhere else. It's an address on our machine, our local machine that we're binding to. And if we read the description, it basically says it. So it says, bind assigns the address specified by ADDR to the socket referred to by the file descriptor. And then address length provides the size. And notice it says, the last sentence here, it says, it is normally necessary to assign a local address using bind before a sock stream socket may receive connection. So we need to bind that to an address. And really, if we didn't call bind, it could bind automatically, but it would just pick a random port and auto assign it, and then we wouldn't know on the client end who to contact, what port they were on. So we really ought to specify or call bind because we want it to bind to a particular port on our particular network interface. Now, the actual structure passed to the address argument looks like this. Notice it has the address family as the first thing, and then an array of 14 bytes of data. Now, in our case, we're going to not use struct sock ADDR. We're going to use sock ADDR _ IN, and it has this divided up a little bit differently with the IPv4. But notice all of them are kind of this. Anytime you use the socket library and bind, even if you're not using TCPIP, you're going to still use this structure. It just changes the way this data is referenced in there. And again, the return value, -1 on failure, 0 on success, just like with the other ones. All right, going on. So that's how bind works. Again, backwards for just a second. Bind looks a whole lot like connect. The difference is this address is not the address of the remote machine. It's the address on our machine and our port that we want to connect through. Okay, listen. Listen essentially listens for connections, and again, the parameters we pass to it, there are 2. And let's read the description. It says, listen marks the socket referred to by socket FD as a passive socket. That means it's going to accept connections. And it says that is as a socket that will be used to accept incoming connection requests using accept. And again, the man pages lead us through all of the things that we need to know if we just read them. And the 2 arguments says the sock FD argument is a file descriptor that refers to a socket of type sock_stream or sock_seq packet. In our case, sock_stream is what we're using. So we're waiting for this connection to come in, sock_stream. And this is the socket that has been previously opened, bound previously open for that. And then backlog, that can be a little confusing to some people. But what backlog is remember we said that one server could handle more than one connection. What backlog is that's the maximum number of pending connections that you can have kind of built up on a queue before a client connecting gets a refused connection response. In other words, if 5 people try to contact my server at the same time, rather than only the first one getting a connection and the rest of them just getting rejects, it'll put them on a queue and then wait for a little bit and say, hold on, I'm in the middle of processing the previous one. But we can specify how deep that queue is. Now again, on success, 0, on failure, -1. And we should be checking those things. All right, the last one of that kind of group of 3 that we said we needed to accept an incoming connection is accept. It says accept a connection on the socket. And notice that accept, this looks the same again as bind and connect, but the meanings of this address and this length are different with accept. And we'll see that here in a second. So going through the description, it says the accept system call is used with connection-based socket types, and that's the type that we're using, sock_stream. It extracts the first connection request on the queue. So in other words, that queue is ordered. It'll always pick the first one that's waiting, the one that's been waiting the longest, and on its listening socket, sockfd, and create a new connection socket. Now that's important. That this is returning to us a new socket that's different than the original one. So this is the listening socket, but once we're connected and accept that connection, it rolls over onto a new socket. And the reason that they designed it that way, rather than just having the current socket be the one we talk on, is so it frees this one up to accept more incoming connections. So that way, let's say a web server that has a whole lot of traffic can very quickly, it's almost like having think of it as having a receptionist who answers the call, transfers it to somebody to handle it, answers the next one, transfers it, answers it, transfers it. But it's returning to us a new socket. And you'll notice it says here, it says the newly created socket is not in the listening state like the original one was. The original socket is unaffected by the call. So in other words, the original one is left to be in the listening state to handle more connections and as many as it wants. And it's spawning off these new ones, like transferring the call to another connection to then handle that, another socket to handle that. All right, so the argument sockfd is a socket that's been created with socket and bound and is listening. We already knew that. And the argument ADDR is appointed to a socket address structure. The structure is filled in with the address of the peer socket. So in other words, when we accept a connection, it gives us this new socket, and we know the address of who it was that connected to us. And that's an important thing. This is not something we're sending to the accept to say what address we want to accept from. This is us saying we send it a blank structure, the length of that blank structure, and it's going to return to us the address of who it is that connected to us. So we can tell who it is that connected to us, the address of who connected. And we could do something. We could say, ignore things from other addresses if we wanted to, only accept things from certain addresses. But this gives us a way to log or do something about who connected to us and know what machine they were on when they connected to us. Now you can pass ADDR as null, and then it will just ignore that return value who connected. So we could pass null, and then we just won't know who's connecting to us. All right, the return value, again, 0 on success, -1 on failure. Okay, so let's look at the server code here. So this starts out very similarly. This goes across a couple pages here, so we're going to go through it. So again, notice that this starts out with 2 sockets, the socket that we're going to listen on and accept connections on, and the new one that it's going to create. So we just created 2 integers up here. We have 2 socket address structures, the one that we're going to bind on, and then the one that's going to get filled in when they connect to us. And then we have this variable, their address size, that is going to be used when the address size gets filled in. Okay, so we create a socket. We did that before. But now rather than connect, we bind. So we fill in our address. Now one thing to notice, if you fill in this address as 0 here, it'll use the default local address. And that can be something that's useful, you can say just use whatever my default network connection is by filling that in with 0. Just use the default. But I still want to have the address family INET, and here I'm using port 1234 in hex. And really, this is just the port I'm going to be listening on. So when somebody connects, they're going to have to connect on that port. And notice I use this H2NS function, the HTUNS function. That stands for host to network short. And that's because the TCPIP subsystem, we need to make sure the endianness of our local machine matches the endianness of the network. So you should always use these functions. On some machines, it's going to leave that number unchanged. On some of them, it's going to switch the most significant byte and least significant byte around to do that. But we should probably always use that function to make our code portable whenever we set the port value of something. Now, after we've set up the address, we bind. So we pass in my socket, the listening socket, the address, and then the size of that structure into that. And after we get past this, if this succeeds, we have now bound to that socket. Now, continuing on in the code, notice that we then have to listen. So we call listen. I made a backlog of 10 on my listening socket. Really simple to do. If we make it past that, we're now listening. So once we're listening, we can now accept connections. So I set the size of their address structure. I pass the pointers to their address and that address size thing into that, along with the listening socket. If I get to this line after this, that means that it is accepted. So if I call this accept and nothing is trying to talk to us, that will block it by default. We can turn that off and make it not block, but right now it blocks by default and it waits. And as soon as a connection comes in, we get this new socket that we can then use to communicate on, which frees this up to be listen and accept more connections. But this new socket is now what we're going to communicate through now that we're connected. Again, think of it like a telephone where the accept just transfers the call to another socket, so it frees up the main line to handle more calls that are coming in on that backlog. Okay, so now we're connected. So we know how to write the client code. We know how to write the corresponding server code. And at that point, client connected. This one accepted the connection. Now we're connected. We now have a communication stream that we can put data in and pull data out of. So to do that, we're going to use send and receive for that. You can also treat them like files and use read and write, but we're going to use send and receive. Really, they're closely related in how they work because they're just sticking data into that thing. But if you look at send, it says sends a message on a socket. And so the idea there is that's what's going to write data into that socket. And then on the other end, we're going to have to receive that data. And we're going to do that with receive. So notice that send on one end of the connection has to correspond with a receive on the other end to get data to go through that. All right, so let's look at those two functions in a little more detail. Let's start off with send. So send, basically, we pass in the socket we want to send on, and then a void pointer to a buffer that we want to send, and then the length of how many bytes that buffer is we want to send. And then there's this flags thing at the end. But what we're going to do with this is we're basically going to pass in the new socket here or the connecting socket on the client end. The reason they made this a void pointer, well, first off, what is a void pointer? A void pointer is basically a generic address. It just says, here's some data at some address. So think of it like a byte array, a pointer to a byte array. But the cool thing about this being a void pointer is we could pass the address of anything we wanted. So if we had let's say a binary structure in memory, and we wanted to have that transferred across the network to the other end, I could just pass a pointer to that binary structure and then the size of that binary structure, and it would send that. Or if I have a string, I could pass a pointer to the string and the length of the string, and it would send the string. Or if I had an array that lived in memory, I could pass the address of the array and how many bytes long the array is, and it would transfer that. So the whole reason that this is a void pointer is it allows us to transfer data of really any type we want. We just have to pass the address of it, and then how much of it there is, and it'll send it. Now, the flags argument can have 0 or more flags. We're not going to worry about that too much right now. For right now, we could pass 0 flags in there, it's equivalent to write at that point. But we'll talk about the flags a little bit later on in the semester. Now, again, on success here, this is a little bit different. On success here, on error, it's still -1, but on success, rather than returning a 0, it returns the number of bytes that were actually sent. Now, this is actually an important point with TCPIP and what trips up some novice network programmers, is that the returned number of bytes might not match the length that we wanted it to send. So for example, if we have a really large buffer, we say, hey, send, I don't know, like 64K worth of data all at once. It's possible that this will return before it finished all of it, but it'll tell us how much of that it sent. So if we have 64K worth of data or 20 meg worth of data and we want to send all of it, we need to make sure that the value that's returned, if it doesn't match length, we need to call this again with a new pointer that's moved ahead by that amount. So in other words, you can build this send inside a while loop that'll say send and keep sending until we get where all of the bytes have been sent and all of the length has actually completed and been accumulated through that. So we might need to call send multiple times to send a large thing. And this ssize_t, that's just a send size type. That's type def somewhere. It has like it's platform dependent somewhat, but it's usually just a integer of some sort that gets returned there, like a long int. Okay, the other end of this is receive. On the receive end, notice it's the same thing. We pass in a socket, we pass in a pointer to a buffer, we pass in a size of how big the buffer is, and then we have flags. And again, except this is going the opposite way. This is a buffer. We want to store the data that comes in. This is the maximum size of that buffer. But notice when this thing completes, it's going to return this size_t, this integer that says how many bytes did I actually receive. So again, if I received less than I expected, I should call receive again and continue building up the data. And this comes back to where we mentioned earlier that we saw that part of the code or the part of the man page where it said that it did not preserve record boundaries. This is where the size comes into play. It can be very important to not have one message run into the next and know where they end. So we have to build in our own kind of boundary system, our own logic to make sure when what I sent, the amount I sent was the amount I received. Again, TCPIP will guarantee the reliability, but it might chunk it up in different ways as it sends it because they don't want to hold on to the data for a really long time before they're releasing it to the application because that could slow things down. So they'll get through what they can when they can, but it's up to us to make sure that we know when one logical grouping ends and the next one begins. All right, so again, the number of bytes received is what the return value is, or if there's a failure, -1. Now, there is one final thing for the return value of received that's important. If the other end has closed the connection, the return value will be a 0. So if the other end performs a shutdown of that socket, then we call receive. Receive will return. It'll say, hey, I received 0 bytes. But that means nothing was sent. That means they closed the connection. So that can be important to look at as well. Okay, so now we've exchanged data. The last thing is after communication is complete, we need to close the connection. So once we're done sending data one way or the other way or both or back and forth between them over time, let's say we're now done with that connection, we want to close it. Easy way to do that is we just call shutdown. In Windows, we do it with close socket. So there's a difference between how we would do this in Windows and how we do it in kind of Unix, Linux. But that brings me to a thing that we're going to come back to later on. Notice most of the stuff works the same in Windows as it does in Unix with the Berkeley sockets library. And we're going to talk about Windows specific changes that are necessary in just a little bit. But let's look at shutdown for right now, since that's what would be in the man page. So from the man page there, in the Unix Linux version of this, shutdown, it says shutdown part of a full duplex connection. Now when we call shutdown, we pass in the socket and then how we want it shut down. And notice there are several methods. There's kind of shutdown for read, shutdown for write, or shutdown for both read and write. So these are kind of pound defined for us. So if we want to close the entire thing, we can shut all of it down. But there are cases where you might want to accept a connection, then only have it be read-only. And if you do that, you can actually shut down and then still shut it down for writing, but still read stuff from it. And again, error value 0 means success, -1 means failure. Now for the Windows version, we use close socket. It doesn't have a how, it just says close it. We pass in the socket, it closes it for us. And it returns a 0 on success, otherwise the socket error is returned, which socket error is -1. So it's really the same kind of function, it's just a little bit different. And then how we get the error, we call this WSA get last error. But we'll talk about Windows specific TCPIP programming in just a second. Okay, so going through an overview and putting all that together, we have a client, we have a server. And notice that a lot of these steps are similar. Some of them are a little bit different, and I left out a step in here to bind to the local address. We still need to fill in some of that address structure information in here, but I left that out in this description so it would fit on the page, and that's kind of implicit in the bind part of this. So in other words, on the client, we first open the socket. Once we have the socket open, we fill in the address of who we want to connect to, and then we call connect. After we're connected, we call send and receive to exchange data however many times we need to. When we're done, we shut the whole thing down. On the server side, it's very similar that we still have to open a socket. We would fill in the address structure, we would bind, we then listen. After we're done listening, we accept, or in the listening state, we can accept connections. Once we're accepted, we're connected, we can send and receive data, and then we can shut down at the end when we're done. So notice a lot of overlap. The main difference is on the client, we use connect. On the server, we have to bind, listen, and then accept the connection that comes in to answer the call. But after we're connected, send and receive work the same way, shut down works the same way, and getting a socket at the very beginning works the same way. Okay, so back to this picture that we had earlier. Notice that the client, socket, connect, read and write, close. Server, socket, bind, listen, accept, read and write. When we're done reading and writing, close. Okay, now programming this stuff in Windows, which I assume is where most of you are going to program it. If you're not on Windows, then if you're on Linux or some other Unix variant, including Mac OS X, which is a kind of a BSD distribution-based version of Unix. Notice that first thing we do is rather than including syssocket.h like we did on the Unix system, we just include winsock2.h. And really, it's just this has the same functions in there. It's just on Windows you import or include winsock. On Unix, sys/socket.h. Now, also in Windows, before any socket functions are used, we have to initialize winsock. And to do that, we create this WSA data type called WSA. It doesn't have to be that. You can make that anything. And then we have to call this WSA startup function. And this make word 2, 2 thing, this is requesting the version of winsock. This is 2.2. And then we pass in the address of this variable we put up here. That then allows us to create what's called the winsock context for the DLL. And if that succeeds, then, or if it fails, it will return something other than 0. 0 is succeed, failure on is that. And notice here, if it does fail, I can actually get the error, this WSA get last error function. We'll talk about that in a second. But we have to do this before we do anything else. So if we were to go back to this, if we were on a Windows program, we'd have a step 0 that's initialize winsock for each of these using this method. Don't have to do that in Unix or Linux. All right, the third difference here is we call WSA get last error function to get the error code rather than using the global variable error no. Which is kind of a Unix-specific kind of way of reporting errors, the last error that happened. But this is kind of the same concept. We just call this instead of using that global variable. The other thing is when we close down a connection, we call close socket instead of shutdown, but it's really kind of a one-for-one change between those two. And then when we're done with WinSock, we have this final step of calling WSA cleanup, which frees the context that was allocated by our WSA startup function. So in other words, going back to here, we call WSA startup. And then at the end, after we're closing the connection, we're done with WinSock, we call WSA cleanup at the end. And do that on both client and server if we're on a Windows machine. But other than that, everything else works the same. And the reason it works the same is that Berkeley sockets on Unix predated Microsoft Windows, and specifically Windows being able to connect to the network. Originally, when Windows was created, it had no TCPIP connectivity in it. That was added later on by this WinSock module, which I remember back when it was called Trumpet WinSock, which was some third party made the Berkeley sockets layer. And then Microsoft pulled it into their operating system. But what they did is they basically just ripped off exactly how Berkeley sockets work, because that's what programmers understood. And it was a good library, good way to interact with networking. And so Microsoft basically just copied it. But they made a few changes here and there. But other than that, it works the same. Bind, accept, connect, listen, all of those functions, send, receive, they all work exactly the same in Windows as they do on a Unix system. So if you learn sockets programming on one platform, it's the same on other ones. It's also the same in other languages. We focused on C, C++ here, but note that sockets programming, the concepts work the same in other environments as well. For example, Python. If you're using Python, if you're doing sockets programming in C#, the concepts are the same. The functions work the same way. All right, so let's finish up by going through a full client example here. And so you notice that this is a Windows thing, so you could build this on in something like Visual Studio, or you could build it in something like CodeBlocks if you want something that's free open source to build it in. But notice that the only things I need to include standard I/O and WinSock 2. So I've included those. The next thing I did is I just defined for convenience this response size of 5,000 bytes. I'm going to use that for receiving data back. But what this program is going to do, I'm going to connect to Google, request the default page, and then kind of print it out on the screen, whatever the data that I got was. All right, so going through this, you'll notice that first thing I do, initialize WinSock. We talked about how to do that. If I get to here, it's been initialized. If I don't, then it's failed. The next thing I do is create a socket. It's AF_INET, sock_stream. If I get to here, I've opened the socket correctly. So this is continued on the next page. Let's go to that. So the next thing I do is fill in the address structure. And again, this is a client. So this is who I want to connect to and what port they're on. And again, there's the use of the host to network short function, the htons function. So I'm saying connect to this address on port 80. And then I call connect. And if I make it here, I'm connected. The next thing I do is this is HTTP specific, but what I'm going to do is I'm going to send this message, say get the root page of that using HTTP 1.1. And then I'm going to receive a reply up to 5,000 bytes long that I found earlier. And so if I make it to here, I've sent the request, I've received the reply from Google, and now I'm ready to print that on the screen or display that. So I printed out how many bytes I received. And now the last thing I do is to that buffer, I added a null character. I print out the reply on the display. And now I say I'm done with that connection. So I close the socket, call WSA cleanup, and then that's it. So this is going to go to Google, download the kind of default page, print it on the screen, and then close the socket. So notice this is what your web browser does. When you say go to google.com, that's what it does. It opens the connection, There's one thing that's kind of missing in this, and notice that I had to know the address to put in here. We could make this work with google.com, but we haven't talked about name services yet. That's another service that's provided on the internet to look up what number goes with what name. We'll talk about that at a later point in the semester. But the idea is we now have the ability to do what a web browser does. We're just printing out the response on the screen rather than rendering it in a web browser. But this is what your browser does when you go to something like google.com. Now, let's also look at a simple web server, which is kind of the other side of that. So this is going to open a port, listen for an HTTP request, and then serve a basic HTML page. So looking at this, include the same two things. I've basically pound-defined what port I want to listen on. And I could use port 80 here, but I used 5050 instead just to keep away from port 80. Since that you might have something running on your machine that already has something on port 80. Maybe not. But I used just this arbitrary port 5050. I set my request size to 5,000. But what this does the same stuff. Initialize WinSock, opens a socket, fills in the address structure, but this is for my server, so I'm using the default address and the port that I pound-defined up there, which is 5050. And then I bind, I listen, and now I'm ready to connect. So now when I get down here and hit the connect and accept that connection, so now if I make it past this, somebody has connected to my web server. So what I'm going to do is I'm going to receive their request. And notice the way I'm receiving that is with receive. So I'm printing out their request, and no matter what they send, and I'm sending back this really simple web page response in HTML format that basically says hello world. That's all that it says inside of there. And it's centered in a heading type 1. Really simple web page that I'm serving back. I send that. So I send that message. And then since this message is so short, notice I don't have the while loop around send, making sure it sent all of it. Same thing on receive. But in this case, I'm just going to assume that's okay. And then the final thing we do after we serve the web page, I close the socket. Actually, the new one that was created, close the original socket that's created, I clean everything up, and then I'm done. All right, so that's all for today. I am going to post a quiz later today on some of this stuff, so you might want to take a look at those man pages for socket, connect, bind, listen, accept. I don't know if I already said that or not. Maybe I did. Shut down. So you might want to look at those. But the idea here is relatively simple. That here's a full working piece of code to compile for that. We are going to have a lab next class also, so you should probably look at that. Here we have a cool animation where I can make that jump up and down. But the idea is that do the quiz today. I'll post that in just a few minutes here. And next class, we're going to have a lab where you're going to write your own TCPIP code that actually transfers some data from one machine to another machine. Or you can also test these on your local machine, have it talk to itself. We'll talk about that next class as well. But the idea here is I want you guys to start getting used to writing this TCPIP code. So we're going to have a lab doing that next time. So until then, stay safe. If you have any questions on anything or anything doesn't make any sense, feel free to send me an email or ask in the comments section. And go ahead and take your quiz later today. Okay, that's it.